Hi all, in this video we're going to prove that gamma of n is equal to n minus 1 factorial, where n is a positive integer. So we're going to start with the gamma function, and actually the proof I'm doing here is different. There are different ways to prove this. One is to go through the mathematical integration, do integration by parts, and it's just a long tedious process, but I think this is easier way of doing it. There is a little catch at one point. I'll tell you what the catch is in order to do this proof using mathematical induction. That's what I'm going to do, use induction to prove this. Now, if you recall, the principle of mathematical induction is to show that this statement is true for n equal, in this case, like 1, 2, 3, 4, and so on. And then we're going to generate our induction hypothesis. And then from induction hypothesis, we're going to conclude that this is going to work for any value beyond the kth value, integer value. So let's start by first our base case, as we call it. Let n be 1. We want to know if this is going to work even. So when n is 1, in other words, we're going to go gamma of 1 is equal to the integral from 0 to infinity of t to 1 minus 1 e to negative t dt. Of course, this part is going to be 1 because t to 0 is 1. And because the limit of integration involves infinity, the upper limit. So this is an improper integral. Therefore, we need to go through limits in order to have actually values for the lower and the upper limit. So this way we can actually do the fundamental theorem of calculus. Otherwise, the fundamental theorem will not be applicable. Okay, at this point, we're just going to evaluate this. So this is going to be the limit. A goes to infinity. And we evaluate the integral. We get the integral of e to negative t is negative e to negative t. The limits go from 0 to a. And now we can apply the fundamental theorem. I'm going to bring the negative, this negative, outside of the limit. So the limit is a going to infinity of simply e to negative a minus e to 0. And right, this step is where the fundamental theorem of calculus kicks in. Now, the limit of e to negative a goes to infinity. Again, just to show you a graph here, this is what the graph of e to negative a, assuming the a-axis is the horizontal axis. As a goes to infinity, the function approaches 0. So this part of the limit is 0. Negative on the outside, negative inside. It makes that positive. And then here we have simply the limit as a goes to infinity of 1. And we know that the limit of a constant is constant. So that limit is just 1 because the constant doesn't depend on a, regardless of what a is. The limit of a constant is constant. And there you go. So gamma of 1 is 1. Okay. And let's see. So that's going to be 1 minus 1 factorial, which is the right side of this theorem, is 0 factorial. And 0 factorial by definition is 1. Therefore, 1 is equal to 1. Again, this was the right side. And this is the left side. So we show the left and the right are equal. Now, in another video, by the way, I show that 0 factorial is equal to 1, this part right in here. I show you formally how that looks like, again, using gamma function. Maybe I put a link to that as a comment for this video. All right, so this thing is going to work, and then you can go through similar process and show that it works for 2, for 3, and so on. Now, once we have this, from here, we go to the next step, which is our inductive step. Okay, so our inductive state says that we're going to say that we'll assume that gamma of k is equal to k minus 1 factorial. We're going to take this to be true. This is called the induction hypothesis. And this is going to be true for, let's say, for some positive k. All right, and that's, remember, we're working with integers. So we're talking about positive integer k. All right, now we need to show that p sub k plus 1 is true. P sub k plus 1. Again, this would be p sub k, stating it as that. And when n is 1, this is p sub 1. Okay, up there. So p sub k plus 1 is going to say that we need to show that gamma of, that's when you change k to k plus 1. It's very simple. And that's going to be k plus 1 minus 1 factorial, which is simply k factorial. This is what we need to show, and we can show that. Then we have proved this by induction. Okay, now here is a little catch that I mentioned in the beginning of the video, that when you use prove by induction, there's a little catch, and here's where the catch is. There is a recursive property of the gamma function. Let me put this recursive property that again can be proved mathematically by definition of gamma functions. Recursive, let's go property. Okay, that's recursive property of the gamma function. Now, what is this recursive property of the gamma function? It says that, for example, the gamma of n plus 1 is equal to n gamma of n. Okay, that's what the recursive property is. Now, in this case, we're going to change our n to k. Therefore, gamma of k plus 1, which is, remember, our inductive, is what we want to show our p sub k plus 1 expression. So gamma of k plus 1, therefore, is going to be k gamma of k, correct? And again, that's based on this known fact. All right, and so what can we do next? Well, from the induction hypothesis, which is this, that's our induction hypothesis, we can actually replace gamma of k by k minus 1 factorial. And k times k minus 1 factorial is k factorial. Again, that's how factorials were defined. And therefore, we just showed that gamma of k plus 1 is equal to k factorial. And that is what we needed to show, remember, right in here. Therefore, we can say, okay, well, this thing is going to work for 1, for 2, for 3, up to k. And by induction method, we're going to say, okay, well, this is going to keep working for all positive integers. So if it works for k, kth integer is going to work for the next integer as well. Remember, k actually is a positive integer. It's an unbounded number. And there you have it. Therefore, the conclusion is that by induction, we have shown gamma of k plus 1 is a k factorial. All right, and this will conclude the proof of what we wanted to prove here. And of course, we want to prove gamma of n is n minus 1 factorial, right? So if we change, again here, if you let n be k plus 1, right? Then of course, k is going to be n minus 1, right? Solve for k. Therefore, gamma of k plus 1 becomes gamma of n is equal to n minus 1 factorial. And that is what we wanted to show. All right, so we're done. Hope you find this useful, everyone. And as always, thank you for watching.